Welcome. This is the second lecture on advanced learning and evolution, and today I'm going to concentrate on neuroevolution, approaches for evolving neural networks, population of neural networks, and a few things about generalization. What's the problem? What are the methods which are commonly used to improve generalization? So in the first part, I will present approaches about evolving neural networks using genetic algorithms with either binary or real value encoding, and on an approach which uses swarm intelligence, a group of methods inspired by nature, and I will present one of the representatives, a representative of this category. It's called particle swarm optimizer. In the second part, I will concentrate on generalization, introduce the concept of VC dimension, which relates the capacity of the models, an interesting theoretical measure, how we validate in practice machine learning models, and what kind of methods we can use to improve generalization. Most of these techniques are already part of the different packages. So the problem with neural networks, as you understand, has to do with the training and selecting the right architecture for the problem. Approaches based on backpropagation have several problems. They cannot guarantee they will find the optimal model. And that's why people still try to find appropriate techniques to search for the best architecture. And this is currently an active area of research. Neural architecture search is called. If you Google about it, you see that it has become, again, with the advances in deep learning, again, part of the research agenda, as it's not so simple to design deep networks, find the right architecture for the right problem and do the training. In the context of evolution, the problem can be treated, can be approached with an algorithm like the one on the slide. So we have to select the proper, the right metric to measure the performance of the network, the error, and there are different ones. Choose a string that represents the different neurocomputational parameters, such as weights and biases. You can even make it more rich if you include parameters about the architecture, like number of hidden layers, number of nodes in each layer, slopes of activation function, etc. Then you generate a pool of strings. These are a member of the population. You evaluate the performance of each member of the population according to the criteria you have set. Sometimes you have to convert that to a fitness and then apply genetic operators to obtain the population for the next generation. That involves crossover, mutation, selection, etc. And this is an iterative process. It runs for several iterations or until you produce a very low error or high fitness. It depends on how you define fitness and whether error can be used directly as a measure of fitness. And here is an example which shows you how the encoding is done when it comes to using genetic algorithms for finding the right weights of a neural network. So this is a population-based method. So we have to initialize a population of potential solutions, which in this case are configurations of artificial neural networks. If we use a fixed architecture, then the problem is somehow simplified. You concentrate only on finding the values of the weights. And on the slide, you can see a small network, 3 inputs, 4 hidden nodes, 1 output. And on the left side is the representation of the weights in matrices, just to help you understand how this architecture is converted into some kind of genes and chromosomes. So in the matrix, you can see the weights from, for example, the node from neuron 1 to neuron 4, and you have a weight 0.9. And from 1 to node 5, and you have minus 0.8, etc. And you see how these are represented in the chromosome. So 0.9 is the first element of this chromosome. Then you have 2 more weights which actually come from node 2 and 3, but they feed node 4. And then you have weights that feed the fifth node. They come from node 1, node 2, and node 3. So this is how we decide on the mapping of the architecture into some kind of encoding in the chromosome. And we initialize our population and we start the process. The next step, would be to find a suitable fitness function to evaluate the chromosome performance. And this function will use to assess the performance of each one of the neural networks, because each one of these chromosomes represents a neural network. And there are different ways to evaluate the performance of neural networks. This has to do with the different error functions that we have, some square error, some mean square error, cross entropy. All this can be used to assess the performance of a neural network and somehow either used directly or combined to form a more complex metric for the fitness. The training sets are presented in the network. The network can be evaluated, and then the information is used to do selection and continue with the process, like the use of genetic operators, crossover and mutation. So the crossover will operate in the normal way. You can specify crossover points, and then you use parents to produce offspring. In the mutation, if you use real values, then the mutation becomes a form of noise, which is randomly injected into the different positions of the chromosome, different genes, and the noise can take values between -1 and +1, because we want weights to be positive or negative, and can increase or decrease randomly using the mutation in a way, in an effort to introduce diversity into our model. And I have an example here. Parent 1, parent 2 do randomly selected members of the population, configurations of neural networks, which can be used as parents in order to produce an offspring. And the process explained in the figure. So you have to map the architectures into chromosome representations following the approach I presented before. So you have nodes 0.1, weights 0.1 and -0.7, as you can see. And these are weights that connect node 1 and node 2 to node 3. So this constitutes the first part of the string, and then you have two more values, -0.2 and 0.9. These are weights that node 4 receives from node 1 and node 2, and so on. And then, depending on how the crossover has been defined, you produce an offspring which has elements whose elements belong to different parents. So you can see the child here. We have the first two elements come from parent 1, the next two from parent 2, and then we have again from parent 2, and the last three come from parent 1. And that will give you the configuration of the child, which is another neural network. And we follow the procedure. We have to evaluate performance, apply mutation, if there is mutation in this case. And I have an example here to show you how mutation works. So mutation will be randomly applied to some elements of the child. So I have the original networks there, and just two elements are mutated by injecting a random noise between -1 and +1. So the values, as you can see, change from 0.4 to -0.1. It's just a scenario, just to show you how things work. And in the literature, there have been different approaches that follow this kind of idea. One method which has become popular is NEAT, Evolving Neural Networks through Augmenting Topologies, it's called. And I have in the slides the link to the article. You can see the details of each operation, how mutation crossover, how they are defined in this case. It also allows networks to expand, so you can add more nodes or you can remove nodes. You can alter not only the weights, but also the structure of the network. And there's a video, YouTube video, which also explains this process. Recently, a package, PyTorch, included a new version of NEAT in Python as part of the PyTorch library that was developed by Uber AI Lab to allow people to use NEAT in order to evolve architectures of deep networks. This is another example where we evolve the neurocomputational parameters which relate to the architecture of the model and to the training algorithm. So it's not about the weights anymore. Here we have a representation that covers 3 parameters: number of hidden nodes assumes that we have just one hidden layer. So we have number of hidden nodes, a learning rate of the algorithm, a slope of the activation function. As you understand, it's very flexible. Someone could create a much more complicated representation for the chromosome and include weights, but also architectural parameters. So it's an approach which makes sense to use in the context of neural architecture search. And also if you want to fine-tune even training algorithms. When you do this kind of approach, you would have to make some decisions about the range of variations that you allow. So for example, in this case, we said that, look, number of hidden units can vary between 10 and 500, learning rates 0.07 to 0.1, slope of activation 0.0625 up to 4. You have to do that because the range of variations relates to the number of bits that you are going to use, especially if you use binary representation. It will affect the encoding that you have. Okay, so you have to make a decision at some point on the range of values that you will allow the parameters to take. This is an example of algorithm which follows this kind of idea. It actually builds on the concept of hybrid GA that I introduced in the previous lecture. Because what it does is that it uses genetic algorithms to evolve architectural parameters and parameters of the learning algorithm of the members of the neural networks, but it uses local search when it comes to train the particular member of the population. In hybrid GAs, we said that we evolve members of the population using the Darwinian approach with crossover, mutation, and selection, but we allow individuals to improve themselves at each generation by applying a local search strategy. So this is what happens here. So you have this kind of approach actually seems to work very well when it comes to generate members, neural networks with an ability to learn different kind of tasks. So that's why you can see you identify the task, you present the different tasks, and then you start the model which generates a population of artificial neural networks. It follows a particular approach to create this kind of population, and you can find more in the article that I have the link at the bottom of the slide. That was recently, it's a new approach that was recently published. But the main characteristic is that we use local search, like in this case, any kind of training algorithm like RPROP or ADAM to fine-tune, adapt the weights of a member of a population, like in a Lamarckian strategy. And then once you do that for the different members of the population, then you can apply criteria with fitness, select parents, apply crossover mutation in order to evolve the members of the population and produce new architectures. This particular approach uses special crossover operators in mutation, which are based on human biology, the meiosis and fertilization processes. So it has copied, the specific kind of approach used in human genes. And the advantage is that, as I said, you can train a population of networks, which at the same time can learn different kind of tasks. And the way they approach the tasks differs depending on the circumstances. So I have just 2 tasks here to show you how it works. On the first row, we have a language acquisition problem. On the second row, we have a classification problem. And you can see how the population members are measured in terms of number of hidden units they use, what kind of learning rate they use, what is the slope of the activation function they use. And you have these bar charts because you involve a population of thousands of networks. It can take, the process takes several days actually in order to do it. In the lab, you will have the chance to work on an algorithm of this class just to for one generation to see how it works. As I said, this kind of process should run in a parallel architecture and will take, if you have, I don't know, 5 different tasks, for example, like in this case, this is just an example of 2, it will take you several weeks to evolve all these populations. But you can see here what happens in the during 20 generations. These box plots contain the members of the population at the generation, and the red line shows you the average behavior. And you can see, for example, how the number of hidden units changes from generation to generation, and it stabilizes around 400 hidden nodes. And you can see that this works for both the language acquisition task and the classification task. When it comes to learning rates, you see that the values do not change that much. You have values around 0.08, 0.085 in both cases. So this is, again, something which works for both cases, for both tasks. In the last column, you will see the slope of the activation function, and here you can notice a significant difference. You see that, for example, in the language acquisition task, the population of the networks after usually around 10 generations moves around to a slope of 0.5. In contrast, for the classification task, the slope of activation is very steep. As you can see, it goes around 3.5. So basically what that means is that you have activation functions with a very steep slope. It approaches, in a sense, the threshold activation function. And this is an interesting outcome because it shows that some of the neurocomputational parameters, the hyperparameters of your model, behave in a way as the so-called generalist genes. General genes refers to genes in the genome which they learn. And through the learning, they can optimize, and we can apply them to different kinds. They are good at performing different kinds of tasks. At the same time, we have domain-relevant genes, which actually are adapted to particular function. And you can see there is some kind of analogy when it comes to parameters of neural networks. Some of the parameters can take values and be used across different kinds of tasks. Some other parameters need to be adapted to the particular context of application in order to produce an optimal behavior. Here is another approach which involves, again, networks, but it uses a group of techniques which are called swarm intelligence. In swarm intelligence, there is a nice video you can look, you can have a look on YouTube with a link. The swarm is based on this idea that you have a collection of simple organisms or agents. Each one has a very simple function to do, but by combining all these organisms together, the collection, the group, can solve some very difficult problems. And this kind of algorithms have been inspired from nature. So, for example, people analyzed how ants, wasps, bees, termites, fish behave, and birds. And then they try to construct similar kind of algorithms. So they construct different algorithms where intelligence emerges by the collaboration of the different members of the population. So it's the interaction between the members of the population and the knowledge that each member of the population collects about local behavior that can help the whole population, or swarm, as it's called in this case, to reach optimal solutions. It's quite interesting because the members of the population and the operators are based on reflect genetic factors, but as well as social interaction between the members of the population. An example is ant colony optimization, which has been inspired by the use by ants. So in the world of ants, you have different ants and they specialized in terms of their contribution to the swarm. So you have ants that protect the queen, they clean the nest, they find sources, food sources, etc. And there are differences in their anatomical characteristics, which implies that genetics plays a role. So you may have small ants that concentrate, they are workers, they clean the nest, they have a specific role to play. There are other ants which are much bigger. They search for food, they defend the nest. And when it comes to social interaction, again, there are different kinds of models that have been used. It can be visual interaction, audio interaction, or chemical interaction through the use of pheromone, for example. And it is transmitted, and it forms a path of communication between different ants. There are situations where the message that is communicated has to do with changes in the environment, so the information transmitted to other members of the swarm. I will concentrate on one method of this class. It's called particle swarm optimizer. It was introduced in 1995 by Kennedy, a social psychologist, and Eberhard, an electrical engineer. It's based on this concept of social interaction and actually human sociology, human behavior. The rationale is that individuals adapt to social norms, and in this way, adaptability normally leads to intelligence, and intelligence emerges from the different interactions between individuals of the swarm. Mathematically, this is how things are modeled. We are talking about search spaces, high-dimensional search spaces, and each member of the population is a particle, it's called in this case, and is represented by a vector. So you have the particle of the swarm, which is a vector and consists of different elements, and it depends how you are going to, the encoding depends on the encoding that you are going to do. If you want to, for example, model a neural network as a particle. So in the simplest case, a neural network is represented by its weights. So these x's here represent different values of the weights, which form one vector, and they represent a particular network. But you have also some other concepts which are specific, unique to particle swarm optimizer. So you have the particle best, which is the best configuration so far for a particular particle. Every time a particle produces a value, every time a particle produces a fitness value, which is better according to some criteria, then that is considered as particles best. Okay, and this is stored, remembered in the algorithm. There are some other terms like the simple nostalgia, which represents the tendency of organisms to repeat past behaviors that have been reinforced, have been proved successful, or return to past successes, basically. So you try something, it works out well. So if the same kind of situation happens again, it's a good idea to follow the same strategy. This is simplified. This kind of concept is represented in a very simple way, basically by an equation like you see on the slide, VT. It's called velocity of the particle, which is based on the previous velocity plus some kind of correction. In this case, the correction is the difference between the values of the particle, the vector xi, and the particle's best. So this kind of difference, because remember we are talking about vector spaces, so you have a difference between two vectors, and this is used as a form of as a velocity, as a tendency for this particular particle to move to regions in the space where previous success was found. And another concept is the best particle of the swarm, particle best, which emulates the success of others. So we have role models, and we try to imitate our models, and this is representing the algorithm by keeping the best particle of the swarm in a kind of list and remembering this kind of value. So particle swarm uses this simple model. Real value encoding does not use binary at all. And this is a high-level description of the algorithm. You initialize the population in the search space. You evaluate the fitness of the individual particles. You modify the velocity by taking into account the best particle, the best position of the particular particle, the best particle in the whole population. This is called global best. There are variants which divide the space, the particles in smaller groups, and each group is allocated a particular neighborhood that they search. And in this case, you can specify a neighborhood best, which influences sense information to the rest of the particles of this particular, that operate in the particular neighborhood. And in terms of equations, it's just two equations. It's a very simple algorithm, which nevertheless is quite effective. So the first equation calculates the new position of the solution vector, which is the position at time t. It takes into account what happened at t-1 plus the v vector, or the velocity vector as we call it. And you can see the equation, the velocity vector. It consists of three terms. One is the previous velocity, which is multiplied with a weight. It contributes, it's a contribution of the previous velocity into the calculation. This kind of weight is called inertia weight. And then you have two more terms. The first term takes into account the individual particle's best position so far. The second term takes into account the global best particle in the swarm, unless the algorithm operates with neighborhoods. So if there is a neighborhood, you have to use, in the particular case, the neighborhood best for the particular adaptation of the particular individual. Because of the nature of the algorithm, the velocity can take very large values. That's why it's recommended to have an upper bound. This is called the maximum velocity of change, to avoid oscillations in the search space. And I have some parameters here. This is for de Jong's test function 1. F1 function, and we use it, I think, in the GA lab as well. It's a very simple function. The global is at the center, and the different dots indicate members of the population. You have a population with 20 particles in this case. And the best particle, it's very close. It's the thick, dark circle. It's very close to the global, as you can see. So it manages to attract the rest of the particles of the swarm towards that direction. And the vectors, the lines here represent the velocity vectors. So you can see how in the particular instance at t iteration 47, what was the velocity of the particle, and the dot shows you the next position that the particle took in that iteration. And it converges after 267 iterations, as you can see. All the particles are in the neighborhood of the global. In this case, the maximum velocity was set to 0.5. The maximum velocity has to do, as I said, with how big the velocity is going to be. So it influences the magnitude, the size of this vector that you can see in the figure attached, allocated to each one of these individuals. Okay, so if you have a large maximum velocity, you may see that this value, this vector, becomes much longer, which means that the particle can jump, make large jumps in the search space. Okay, sometimes it's useful because it allows the particle to explore huge regions of the search space. Some other times, especially when you are in a good neighborhood close to the global, that can cause disaster. It destabilizes the method and can lead to oscillations, and you can miss. You can diverge. The algorithm diverges, and you miss the solutions. That's another example, the Zong's F5 function, which has several local minima, and it has also global. And you can see the situation. The problem is much it's more complicated. It takes longer for the algorithm to converge, but they managed to go to find the global after 1,000, approximately 1,000 iterations. These slides give you an idea of what I mean with the impact about velocity and why it's important to decide how we are going to bound it. So it's the maximum distance a particle can travel. It affects the size of the correction, basically, which is in this case the velocity vector. And you can see for the same problem, two different choices. On the left side, maximum velocity is 2. On the right side, when maximum velocity has been set to 10. So it's the same problem. We saw that the algorithm was able to converge within 200 iterations. If you have a maximum velocity of 2, then it will take much longer because the particles can travel bigger distances, and instead of converging into the global, they spend more time searching the whole space. And you see the size, the length of the vector actually. This tail for behind each one of the particles. So it takes around 900 iterations instead of 200. And the situation becomes a disaster in the scenario at the right side. Velocity, max velocity is 10. That causes serious problems. The particles oscillate. Although you have the global, it's the red cross, and you have the global. This is the best particle in the swarm, the global best, which is very close. Nevertheless, the swarm cannot really converge because of the maximum distance allowed to each particle to travel, and that causes serious problems. After 900 iterations, you see how big, how long the velocity vectors are, which prevent the particles from converging into the promising neighborhood where the global lies. There has been a lot of work to fine-tune some of these parameters that the method uses. It's a heuristic procedure, so there are certainly certain heuristics like C1 and C2. These are two parameters which control the magnitude of the contribution of the particle best and global best. In general, the advice is for these two values to be no bigger than the sum of two values, no bigger than 4, and that guarantees the stability of the algorithm. There has been some theoretical analysis, and people have introduced a parameter called constriction factor, which manages to automatically tune depending on the value of C1 and C2. And the inertia weight, which is used to control the contribution of the previous velocity, it influences how the search will go. So we want to have freedom to explore the whole space, the whole region, but at the same time, we would like to take closer look at local neighborhoods, explore better the local space when we are closer to the neighborhood of the global minimizer. So there is a trade-off there between global and local search that we have to take into account. The method was first used in 1996 to train neural networks. You don't need to use backpropagation at all. You can do the whole training through particle swarm optimizer with a particle swarm optimizer, which means that you don't care about derivatives. The algorithm does not use derivatives. And you can also introduce extra parameters if you want to change the structure of the whole network, not only the weights. And there is work in this area actually recently to automate the parameter selection for deep neural networks. And also solve the problem of neural architecture search, deep neural network architectures for image processing. I have the links at the bottom, and you can see the paper. The second one is specifically about image processing. So how you can use particle swarm optimization to evolve different aspects of the architecture of a deep network, targeting image processing, image classification tasks. You can evolve the weights, you can evolve the slopes of the activation function or other aspects of the architecture. It gives you more flexibility. And as I said, there is recent work towards this direction, as the problem of finding the right deep network and train it. It's not very simple, especially if you want to reuse components in different kind of architectures, different kind of tasks. So we are going now to the second part, which has to do with all these problems with overfitting and generalization, which still are open, and there is a lot of research in these areas. It's extremely difficult to find theoretical, mathematical, theoretical solutions with definite answers for these problems. I'm going to refer to some theoretical works which try to provide a mathematical analysis and theory to explain some of the behaviors we observe with certain classifiers. And these are quite useful because they can be used, as a guidance for practitioners. They can use it when they design, they try to create new models or train these kind of models. So on the slide, you can see some of the open problems, some questions. It would be great to have answers for these questions. Sometimes we have, but for very specific problems or very specific architectures or models. One of the important concepts is the VC dimension, because it relates to the capacity of a classifier, the ability of a classifier to solve a problem and generalize well. There has been theoretical work, but mainly for binary classification. So a binary classifier, basically what it does is that no matter what kind of model you are going to use, neural network or some other technique, it basically implements a function. It's a function, a kind of mapping from the input space, the data that you have, into binary space 0, 1, because it's binary, so there are only two options. But in general, because we can create different kinds of classifiers using the same data set, for example, with neural networks, you train the neural networks. As the weights change, you come up with different configurations, and everything seems to work fine for the same kind of data set. So you have F capital, a set of all functions that the classifier can realize. Okay, it depends on what kind of architecture, obviously, it has and what kind of values the weights can take. But in general, one type of classifier with fixed architecture, no matter what kind of weights you will use, if it's successfully trained, it will produce one of these F small functions, and the set of all small F functions will create a big set of F capital functions. So according to the VC dimension, the VC dimension is the largest integer for which a class of functions, F capital, can achieve all possible dichotomies, 2 to the power of k. K is the value of the integer. This is because we are talking about a binary classifier, and you remember that when we do binary classification, I had some examples in my first lecture, neural networks, like the perceptron model. Basically, what the perceptron does is that it divides with one line the space into two classes. So it's a kind of binary classification. All right. But as I said in that lecture, and we have seen in the labs, there are many different lines, decision boundaries that can be produced. It depends on what kind of values your weight take. So there is a set of functions that can be implemented, dichotomies that can be implemented, depending on the values of the weights that your perceptron model has. So the VC dimension says that, look, VC is the largest integer for which the class of functions F capital, which contains all the possible functions, all the possible dichotomies that can be realized, is specified by this number, 2 to the power of k. In practice, not all dichotomies can be realized by the set of functions because there are values which cannot be reached. It depends on how you train your your model. So not everything can be realized. If you could produce, if you can create a kind of set of functions and the same number of dichotomies depending on the number of data points that you have, and that's 2 to the number of to the power of n. So if the VC dimension is specified by 2 to the number of n, then we say that the VC dimension is infinite. But as I said, we don't know whether it's not possible to have all these dichotomies in practice. Okay, so mainly this is a theoretical limit, I would say. But in theory, it is considered as a measure of the capacity of the classifier. And what practically means is that if the number of training points exceeds this number, the VC dimension, then we can expect good generalization performance. Okay. It takes the metric takes different representations, different realizations depending on the model. Sometimes it relates to the input dimensionality, how many inputs, how many variables you use, how many features you use. Some other times it relates to both dimensionality and the number of parameters that you have, like the number of weights, for example, in the neural network. And people have done theoretical work. They have found some dimension for some of the models. So a perceptron, the VC dimension of the perceptron depends on the number of input dimensions plus 1. For multilayer networks with hard limiting activation, not activations that can be differentiated like sigmoid or ReLU activations, you can see it is bounded between these two numbers, which depend on the number of hidden layer nodes, the total number of nodes of the network, the total number of weights of the network, the number of input nodes. All these parameters play a role in order to define the VC dimension. And the practical advice is that, look, you need to have at least 10 times the number of weights if you want to train successfully a network, for example. Okay, in terms of training patterns, okay. 10 times the VC dimension, 10 times the number of weights, okay. Because as I said, the VC dimension is not so easy to find. So this is the lower limit in a sense when it comes to training. There are several problems, of course, where it's not possible to have this number because the data point is a result of experiment or comes at a very high cost, which limits the number of data points that you have and you can use for training and testing, which affects obviously the training performance and the generalization. When we are using this kind of data, the training data, and we successfully train our classifier, then one of these F small functions is implemented by our model. And we know that our classifier has some kind of error. We call that training error. In theory, this is called the empirical error because it is based on a small set of training samples. The aim is to test with unknown data, we say. So these are data outside the training set. And this is what we call generalization. This kind of generalization, it's an attempt to approximate the true error probability of our model. Okay, we call it generalization error. So depending on the classifier, depending on the values of the different parameters, our classifier will implement one of these f small functions. All these classifiers will belong to, will produce different functions. They all belong to the big set F capital of all functions that can be implemented. And ideally, what we would like to do would be to find the best classifier, the one with the minimum error among the ones we have in this set. So what theory has shown is that if you have a large number of training points and capital, then the empirical error is close to the generalization error with high probability. And this generalization error for the optimal model amongst the ones you have trained, it's very close with high probability to the true error of your classifier, how your classifier will behave in the real world. Okay, so that makes sense. That's why we try to use large data sets. And if you have large data sets and if you train different models, then you have better chance to select the optimal, or I normally prefer to use the term best available. It's the best from the available models that you have. It's very difficult to prove that this is the optimal model. Okay. And on this slide, I have summarized some of the theoretical results which I thought are very interesting, because basically they can be used, they are used as guidelines when we train models, and different packages actually have by default implemented this kind of guidelines because there is a theoretical basis behind it. So the first one, for a large number of training points, the probability of having large differences between empirical and true errors is very small. Okay, so basically that guarantees good generalization if you have a large number of training points. The second point is something which I already mentioned. If you have a large n, you expect with high probability that the empirical error, the performance that you have of your classifier that has been trained with the data to be very close to the performance of the optimal classifier. Okay, the optimal classifier over the specific class of functions. Okay, so it is possible, to find the optimal classifier, the optimal model that you can produce with this particular, for example, specific architecture. Let's say you have 10 and 100 hidden and 2 outputs. There are many functions that can be implemented. There are many different classifiers. If you have a large n, then a large training set, then you have a very good chance to find a classifier which will be very close to the optimal classifier that you can have over this particular class of models. Okay. Number 3, classification error probability of a classifier designed again based on a finite set of n training samples is larger by an amount, delta n, it depends on the number of data points that you have, than the error of the same classifier designed using an infinite set of numbers. Basically, that tells you that, okay, having a limited, a finite set of training samples, which is large enough, it's not a bad thing. Okay, it will help you to produce, a very good classifier, approximate the ideal classifier, which is obviously the one which has a huge and enormous set of data. to use. Okay. And the main advice comes in the last sentence. If you can keep, if you want to keep the mismatch delta n within certain limits, then the number of training samples must be a number of times larger than the dimension of the input. This is something that we do in practice, and there is a theoretical justification actually for that. The fourth point is about keeping the number of training points fixed and increasing the dimensionality of the input. So this thing, it may work up to a certain point. When you reach that point, then any further increase will produce an increase in the classification error. Okay, we call that in practice the curse of dimensionality. Formally, it is known as the Hughes phenomenon, based on the author of this paper, 1968, who first identified the problem and presented it theoretically. And finally, the fifth point, which basically finally explains the situation that people have observed in practice. So you have a classifier, you use, I don't know, 5 features, you have already some performance, you decide to measure some extra information, so you increase the dimensionality of the input space, and you find out that, you know, actually without extra additional without increasing the number of training of data points, you find that the performance has been improved. Okay, so this seems to theoretically contradict, for example, that the point number 4, that by increasing the dimensionality of the input, keeping constant the number of training points will increase the error. This is because in practice, actually depends on also on the not only the dimensionality of the input, but also the discrimination power of the features that you add. So it's a combination of the size of additional features and their power, their ability to increase the discrimination power of your classifier. So this is a situation that people have observed in practice, but only recently there has been a full mathematical analysis of this phenomenon. So I have the paper here in 2020 in the Journal of Classification, and that was only done for a particular type of classifier, LDA, linear discriminant analysis. In practice, you know, we use deep networks. They are nonlinear. It's extremely difficult to prove this kind of situation, although we experience the ability of the capabilities of these networks. We have been able to solve problems that were extremely difficult to solve, you know, I don't know, 6 years ago. Now we can provide interesting results. There is no detailed mathematical analysis, mathematical proof of this kind of behavior. There are experiments and people try to understand exactly what kind of representations they are produced and what is the role of the different layers, etc. But this is purely empirical. As far as I know, there is no full bulletproof mathematical analysis of the behavior of these networks. So what happens in practice? In practice, we are using different techniques to evaluate the ability of a model to generalize. These are techniques people use across different machine learning models, not only for neural networks. And I'm sure you have heard about these terms, like cross-validation is one of the most popular techniques. And you can use cross-validation. You can even use it with the validation set as part of the training. But you can also use it as a technique to test your model so that you can get an estimation of how it performs with unknown data. Another approach was very popular and still it's used because it's hardcore. It's the holdout method. You train a data set and then you have a separate train set And this is what you do. You don't do cross-validation. You don't do these kind of things. You use a separate test set, and this is how you assess performance. Actually, what is advised is that even if you use validation, keep a separate, completely separate test set to make a final check, and do not test on the validation. But nevertheless, the popular method is the k-fold cross-validation, where you have a data set, you divide it into different folds depending on the k. K5, K7, K10 is used depending on how big your data set is. So you have, if you have K5, then you have 5 folds. You use 4, randomly pick 4 for training. You test on the 5th, on the remaining one, and you do that 5 times if you have 5 folds, and then you average the results. And this is how you estimate the validation, the generalization ability of your network. These techniques work well, and there has been some work has shown that in this way you can approximate the true error of your system, of your model. When it comes to particular applications, we may use an extreme form of k-fold, which is the leave one out. And depending on the situation, if it's medical problem, for example, then you can leave one patient out. So you have data, images, exams from a patient. So you leave all this data out. You don't use it at all for training and validation. You just use it for testing with leave one out. So every time you leave a large number of data points that represent just one patient, for example, and you test with that. And that shows that this kind of approach produces good estimates of the true error of the system, because your system is going to operate on new patients with unknown, won't have any kind of information about their exams or images if you use MRIs, etc. So how we validate the performance of our system? We want to estimate in general the error probability of the design system. And normally we use different kind of techniques like this one, error counting techniques. So you have trained your system and you have a test set, a set of test points. We assume that the test data are independent, and they are also independent from your training data. And if you have multiple classes, like in this case, you have M classes and you have NI data points from class I, and you use that for testing, and you can calculate the probability I, which is the probability of error for each one of your classes. And you can do that by using the binomial distribution. So you use the binomial distribution to find the probability of ki vectors from your class omega I to be wrongly classified. Okay, so what is that probability? Is it high? Is it low? You can use it, and you can you would like basically to maximize this probability, because you are looking for the worst case scenario. That's the idea. Okay, to have a reliable system. So you would like to maximize this probability. And maximizing the binomial distribution gives you ki over ni. Ki is the number of points, and ni is the number of data points of this class. So you can count the number of errors divided by the total number of test points in the class. This can be used theoretically to estimate sufficient number of test points for a class. So, for example, if you want to produce an error which is 0.01, then according to this formula, you could use about 10,000 points. If you want 0.03, then you need 3,000 points. Okay. So you can get an estimation of the number of test points that you need to make an accurate estimation for each one of the worst case performance for each class. Uh, in practice, okay, you know, it depends on the data that you have and whether you can follow this kind of guidelines, obviously, and you know, sometimes it's not possible because you have a limited number of data points. And in general, people try to use large data sets, documentations in order to be able to exploit all the information available. Another idea is to use, if you have limited data set, to use the resubstitution method. So you use basically the same data for training and testing. We try to avoid that because we know that it underestimates the true error. Okay, if you do that, you will find, you know, good results because with training you can optimize your model, but that would give you an overestimation of the performance of your model. Uh, if you use a very large n data set size and large ratios of data over the dimensionality of the input space or the feature space, then the estimation gets better. So if you have a huge training set, the estimations that you are going to get and they're going to be better than approximate the true error that your system will make in the real world. The holdout method, it's an old technique still used a lot. It works well. The problem is that you have to divide your data into training points and test points, which means that you have less data for training and testing. Okay. That's the leave one out, which I mentioned already. So you keep a sample out, or you keep, if it's about medical data, a subset, which represents, for example, a particular patient out, and you use it for testing, and you repeat that. You do it for a different patient every time, and then you average by counting the errors. So you use more data for testing and training, and there is some kind of independence. But of course, as I said, the complexity is higher, and we cannot, maybe it's not the suitable method for each kind of a problem, basically. But generally, medical problems, this is the best way. Finally, some techniques to improve generalization, and these methods, these approaches are not new, but during years they have taken different shapes. There are different variants. I'm just covering the basics here, and they have become very popular again with the advances in multi-layer neural networks, deep learning, and the search for the optimal architecture and for the automation of the process of network construction and network optimization as you train, basically, at the same time. So there are approaches which belong to this group of pruning techniques. When pruning is about a set of methods that actually remove weights without hurting the performance of the network. And normally this leads to better generalization and faster training. There have been different approaches. There is one way is to try to eliminate, that's the basic idea, very small weights. Of course, you have to define what you mean by small. So you have to have a criterion to judge whether the value is big or small. There are techniques like that use stochastic criteria, randomness, like dropout. So they just remove randomly weights part of the network. There are other techniques which try to assess the sensitivity of the weights to the solution, which of course requires some way to measure what we mean by sensitive. I have some examples, an example to show you of a method for this of this class, which basically deletes weights that finds that they have no effect on the solution. It uses backpropagation and then quantifies the contribution of each weight by measuring something which is called silency. And then the reduced network is retrained to obtain the final solution. I will explain this method. It's called OBD, optimal brain damage, in my next slide. Another idea is to remove nodes which have lower relevance. We need to define again what we mean by relevance. It's a difference in the value of the cost function without the node and with the node. So it's again another way to assess the sensitivity of the solution to some values, to some weight values. That's the optimal brain damage, a method proposed by Lecan, which measures the saliency by this product. This delta epsilon, delta E here, it's actually an approximation. It's the second derivative. Okay, and this is the weight ji to the power of 2. And this is how you can measure the saliency of the weight. So this is the second derivative is a measure of sensitivity of the cost function to small changes in that weight. So the sensitivity is measured in this case by approximating the second derivative. Formally, it's the second derivative. You have to measure the second derivative, but you understand what that means. Calculating second derivatives is not an easy task. And for a large network, can become very complicated. So one idea is to have an approximation by introducing small noises, perturbations in the values of weights, and then measuring how much the cost function changes and approximate. That's the optimal brain damage. In the same line, other techniques that take into account the size, the magnitude of the weights, and they try to remove some of the weights, like the weight decay and weight elimination methods. Basically, what they try to do is that they try to penalize complex structures. And they do that by applying a penalty term, it's called. It's a general idea in optimization. It's not only for machine learning. So you have an extra penalty, and this penalty, as you do the optimization, it favors certain combinations of parameter values. In this case, it favors simpler structures. Okay, so they take into account the weight magnitudes. And this is one of the first methods introduced, that is called weight decay. I think weight decay, for example, it's available in different packages. MATLAB has weight decay algorithm, and I think there are other packages which use these kind of techniques. So the method tries to use a penalty. So you have the normal form of the error, which is the first term, plus an extra term. And this extra term, it's called the penalty term. You add it to penalize weights which get so this penalty term tries to penalize non-zero weights. The whole approach tries to encourage near zero weights, so that all the values, there is some kind of symmetry in the network. All kind of weights have small values which are positive or negative around zero. So all the nodes of the network contribute equally to the decisions. There are no nodes which are in saturation, locked into particular kind of states, and cannot contribute to the final decision. Okay. There's another idea which is called the weight elimination. Again, it's a penalty term. It's slightly different from the previous one. If it takes into account W0, this is a fixed weight. It's like a normalization factor. So you can have a value which is, again, I don't know, 1. They recommend it in practice. So for a value of 1, if WI is much, much bigger, then the penalty goes close to unity. And basically, this kind of penalty counts the number of weights. If the number of WI is much, much smaller, then the fixed weight, then it takes the penalty term, it takes into account, it works a bit like the weight decay criteria. But it eliminates the small weights, okay? That's the idea. These kind of techniques operate, and they can help. They can be used as regularization terms to improve the search for the weights, and in this way produce more balanced structures, okay, basically. And if you have a balanced structure, you have a greater chance to produce your model to have a better generalization. That's the general idea. So this is the final slide with the material that I used, and I would advise you to go to the sources and for more details about the concepts that are presented in this lecture. So we have the core text, which is Nektevisky, the particular section. This is the article that I mentioned with hybrid genetic algorithms for evolving the population neural networks. The pattern recognition book has the material on validation, generalization, which I used, a couple of articles, one about pruning and another one about weight decay. And this one explains pruning and the use of penalty terms. There are different algorithms which use this kind of concepts. So you have the basic error function plus an extra penalty term, and depending on how you formulate the penalty term during optimization, you can penalize different aspects of your architecture. And finally, on swarms, there is a very nice overview, an article which presents particle swarm optimization and the different variants by Riccardo Poli. You can, it's free online, you can download it and use it. Thank you very much, and I'll see you in the live session. Bye-bye. But before finishing, just one slide to explain what's going to happen next week. So next week is going to be the final session for this term. I'm not going to introduce new material. I will spend the first part of the session, of the live session, to discuss the revision test, the model answers, and common mistakes that people did when as they tried the questions. And then I will, in the second half, I will talk about the coursework, explain the coursework is for MSc students only. So if you're undergraduate, you might only be interested to attend the first part, where I'm going to talk about the revision test, the model answers, etc., and about the second revision test that I'm planning to do after the end of the module. So the coursework is about MSc students, and we'll present it and answer any questions you might have. So it's a good idea to read the coursework brief before coming to the lecture next week. Okay, bye.